Right, so, ladies and gentlemen, coming up next, we have Professor Asim Tewari. Asim Tewari is G.K. Deva Rajalu Chair Professor in the Department of Mechanical Engineering and Head of National Center for Aerospace Innovation and Research at Indian Institute of Technology, Mumbai. Prior to this, he was a staff researcher at General Motors Global R&D Center in Bangalore. He graduated with a B.Tech degree from IIT Kanpur, followed by MS and PhD from Georgia Institute of Technology, Atlanta, USA. After his doctorate, he was briefly with the National Aerospace Laboratories, Bangalore. Subsequently, he joined IIT Kanpur, where he served as an assistant professor before joining General Motors Global R&D Center in Bangalore. Please get your hands together, ladies and gentlemen, as Professor Asim Tewari joins us on stage.
Well, good afternoon, everyone. I guess this is something which is very unique in the sense that we are in a technological revolution when we don't even understand as to what is driving this revolution. It's reached a level where it has become almost autocatalytic. You would be surprised there's one camera which is video recording us, but there are at least 20 other people in the room who are recording us live. And whatever is being recorded, many of us are broadcasting it live on the net. And as we speak on the net, the data is being transcribed, understood, not by a human being, but by an artificial intelligence system, which is tagging each and every event along with the faces and the data which we are saying. But this is just the tip of the iceberg. This is the second day, the last session of this 2 days workshop. All of us who have assembled here from various locations in India and abroad are very well known to the system, and I'll talk to you about as to what that system is. The system is aware of our presence here. It is aware as to who is sitting with who traveled here when, who was actively listening to the talk, and who was on their cell phone replying to a Twitter or a Facebook call. And now this is something which is unprecedented flow of information and an intrusive information which is sitting right in our pocket. This is a phenomenal opportunity, but at the same time a phenomenal threat. And that's basically what I'm trying to get to in the next 25 minutes, that we are in a very strange time and we have to be really very responsible and aware of the challenge as well as the opportunity which this time poses to us. So I'll be talking about smart manufacturing. I'll probably spend just quickly a few minutes on a center which I head, which is National Center for Aerospace Innovation and Research. And this center is primarily there to give and develop progressive, advanced manufacturing aerospace technologies and to develop the ecosystem. And I heard a lot about ecosystem in the panel discussion before. So now what happens is that aerospace, unlike automotive, is extremely stringent, especially because of the certification processes. And we work in that area. This is an industry consortia which is helped by our industry partners, the Boeing, HAL, Sandvik, DMG Mori, Efton Chemical, and many other industries which are not directly our partners but are associated with us. This center works in 4 different areas: machining, composite manufacturing, additive manufacturing, and data analytics. So primarily what I'll be talking about will be something to do with the data analytics aspect. Of course, all of these things are required for a tool room, for a tool manufacturer. The center is headed by me along with a group of my colleagues. We have a lot of direct employees who are working in our center and students who look at the center. And there are various groups in the center: machining group, advanced composite group, mechanical design group, cyber physical systems and engineering group, and each of the group is headed by a group manager and individual contributors underneath. And the kind of work which we do is that we perform research which is very applied in nature for the industry, and it could be in basically these 3 modes: exploratory, long-term; innovation, which is kind of short-term; and developmental, which is really short-term, less than 1 year. And the basic idea is that developmental innovative research is what really applied industry is looking for. The first part becomes almost like a futuristic, a high gain but high risk research. This is just one slide on the kind of machining technology and machining aspects we have. So we have very advanced tools to do in situ dynamic force measurements, looking at the characterization of the tool chip, looking at temperature distribution, looking at high-speed camera and other aspects. So this is the machining research group. Composites, we have both liquid resin transfer molding and autoclave processes. We do machining of composites. We have modeling of composites, spring-in, designing of components. This is a LRU tray. This is an avionics tray which goes into the cockpit of an helicopter. We also develop scientific tools and softwares. So this is a 5-axis milling simulation tool. And then this is the additive group, which has just very recently started. We already have a metal printing facility, and we are looking at a metal additive and subtractive facility in the near future. And of course, all of these put together, we really come to the final aspect, which is what I would like to talk about, is the cyber physical systems and the data analytics group. So this is a group which is relatively new. We started about 8 years back. However, this group is only 4 years old. And in the recent time, it has become extremely active. And there is a very large set of people who are ready to join. Attrition, of course, is a very big issue for us here. People join, they stay for a year, and they leave. So the basic idea which I would like to express as to what really is this data analytics group got to do with manufacturing, and how is it related to the opening statement which I had about we being observed, our data being transmitted and it being read. So essentially, if you think about it, there is a bigger concept beyond manufacturing which is happening in this world. More than 60 years back, there was a term which was derived, which was coined up, known as artificial intelligence. And that became a realm of just science fictions. It was never really thought that artificial intelligence could be more advanced than humans. However, since 2011 and onwards, or 2009 onwards, we have realized that that was completely untrue. Today, artificial intelligence is capable of activities far better than what we can. There is almost no activity, barring few natural language processing activities, where humans still have an edge over artificial intelligence. Otherwise, artificial intelligence has beaten humans hands down. And this artificial intelligence in the context of manufacturing is what we talk about smart manufacturing, in which I want to kind of give you an understanding over here. So this is our understanding from our center as to what we see would be the way forward in smart manufacturing. Several call it connected industry, industry 4.0. So the basic aspect we feel are the following 4 stages. And this is the driver in terms of the technology driver. So the first thing is the data. So the biggest starting point is the data, then processing of it and analytics. And these are the technological drivers. Whereas that is really what you will be getting back. So why would you like to go through this? I'll tell you in a second. But just to explain as to the 4 aspects, so the first thing which we feel is the one which really is already happening, but needs to happen in the near future, is the informative control aspect of smart manufacturing. What is informative control? Informative control is something which provides you an overall 360 view of your shop floor, of your manufacturing facility, real time. You can probe into any specific machine. You can probe into the bearing condition of your bearings. You can probe into the predictive life of your tool. You could essentially look what really is happening, which you could do probably from a shop floor or probably even beyond. You can't really see if the bearing is fine or not, but from this you can. You can figure out what is the temperature and all those aspects. So that is the informative control. So we have unprecedented level of intrusive sometimes understanding and sensing into these systems which otherwise never existed. There was a very big problem that you don't want to volunteer data when you are on the net. But have you ever realized that you have Alexa sitting in your home and you are speaking? Whatever you're saying is being listened by someone, and actually you have bought that to listen to your conversation. Today you have brought a spy in your own room, in your living room, which is listening to everything which you say. Now that is of course an example in the real world, but in the context of manufacturing, you have sensors, you have current sensors, humidity sensors, vibration sensors, acoustic sensors, temperature sensors, which are embedded in your machines, in your tools, and various other locations, which are giving you a complete 360-degree understanding of your complete shop floor. You could have a complete virtual cyber twin of your industry, and you can go to any specific detail and probe and see what is happening without actually being there. So that is the first level, informative control, and that is something which has already started. And this will be the first step which will be adapted by and adopted by this nation. The second aspect comes, which is known as reactive control. Now, to some extent, reactive control existed in the past. There are CNC codes which will look at chatter and will avoid chatter. based on the real-time data which they're getting. So that is nothing but reactive control. But now the reactive control has been taken to a next level. These initial chatter and other aspects which you could reactively control were based on physics. But now this is a complete different paradigm shift. Reactive control based on data. You have no requirement of physics, you just can have data given to it and it will figure out any complex reactive aspect. Now this is something which also will work in real time. I'm looking at less than 200 milliseconds or even smaller, depending upon, of course, your requirement. So it could react to something in a fraction of a second and take a corrective action. So this is the next level, and we already have some specific aspects of this in the industry. Then comes the third stage, which is still at a very early stage in many cases, which is predictive control. Now in reactive control, when something happens, you react to it. However, in predictive control, you react to it before it happens. So you don't have a heart attack and you take the patient to a hospital. You say, hey, you know what? In 3 days from now, you'll have a heart attack, you better go to a hospital. Now that is the capability which we have. And this is not based on physics because the physics makes the system very complex, but it's all driven by data. Now this becomes, as you go from informative to reactive and from reactive to predictive, it becomes more and more specific. I cannot give you a solution which will be a generic solution for predictive control. If you want to predict the residual life of your tool, you need a specific kind of solution. On the other hand, if you'd like to predict the life of your bearing or the life of your spindle bearing, there'll be a different kind of solution. So the solutions become more specific, whereas informative control was a little more generic. You could take one solution from one company, one shop floor and apply it to the other and it will work. And then comes the last part, which is prescriptive control. Now, if you see the first three things, you had applied. Informative control was something which you could do based on what has already happened. Reactive control was something which you did based on what was happening right now. In applied and predictive control, what happened was that you did something before it happened. But once you come to the last case of prescriptive control, you are not really required in the loop. Human in the loop is not required. The machine, the smart machine understands, predicts what's going to happen, and prescribes itself a medication. It is that you get to know, well, you are going to have a heart attack, and then you describe and you prescribe yourself a medication and you correct yourself. So now the human in the loop is gone in the last part. And that is where your cyber twins will become completely autonomous. Now, in some sense, this has been happening for several years. This has been happening for several years. Your printer, when it goes out of cartridge or it out of toner, it sends an email to the supplier that please supply me a toner cartridge. If you are really requiring your printer or something is requiring maintenance, it can send an email to the supplier provided you have switched that on. But this will be far beyond that. You may not ask it to do some specific corrective actions. You could give it a broad guideline. I want my productivity to be at 80%, or my breakdown time should be less than this. Do whatever is required to do that. It will go through the informative, reactive, and predictive, and then understand all of that and prescribe that if you want uptime to be more than 80%, 90%, then I need to have 3 of these tools in stock. I need to have this in stock. It probably will be in a position to even allocate human resources. It will say, you know what, I need to be running in 3 shifts, and these are the 2 operators who behave the best for me, so I would like them to be there rather than the others. Now we are at that situation. So this is the bigger map of AI being used in manufacturing. So what is a smart manufacturing? What is Industry 4.0? It is nothing but usage of advanced AI in manufacturing. To be now more specific, you can't do this unless you have some basic tools which let you do this. We had these sensors. There has been no real major change in sensors. There have been more sensors which have come in the recent years. They've become smaller, they've become smarter, they've become more responsive, they have higher frequency. But the key differentiator has been the machine learning. The way the machines learn has completely changed the way we handle these physics problems. There is essentially a tussle going on between physics and data-driven mathematics. Mathematics says I don't need physics. I don't need to know F is equal to ma. Just give me enough data of a ball falling and I'll figure out what would be the case when you have a big moon and maybe a comet coming to you. So now this is a fight which is going on between the physics and the mathematics, and that is all driven by machine learning. And these are the classical techniques of machine learning: the informative control, the informative-based learning, similarity-based learning, probabilistic learning, error-based learning, and of course, expert system-based learning. However, the key change which has happened is this deep learning. In about last 10 years, this field has really changed the way we think about AI. It's the resurgence of a new species. It is a species which is so capable and so potent that it can actually be the dominant species of this planet. Humans will no more be the dominant species. That is possible, and that is this deep learning. The convolutional networks, the recurrent networks, the fully connected networks, they have changed the way we actually process data and the way we can predict. Coming back to the specific details of what my center does in this area. So we look at a very large set of possibilities, and this is just giving you an overall picture of that smart factory concept. So we have our own IoT devices which we design, fabricate, deploy. We have the firmware written by us, we have the communication protocols written by us, we have the code running at the data analytics servers which are written by us, and we have the front-end GUIs written by us. So we have a turnkey from the device development, fabrication, to the deployment and getting the analytics done. And these are the basic areas which it looks at. It looks at plant operation and monitoring. It looks at equipment condition monitoring, tool wear monitoring, adaptive control, and total quality and production monitoring. So this is what we are right now doing at several pilot studies in aerospace companies in Bangalore and in Pune itself. And this is just a screenshot of how the data is flowing in, and this is our CNC machine where the data is being shown. Of course, this will be all not shown to the end user. The end user will only have specific actionable items available to them. And the overall architecture remains pretty much the same, that you have a shop floor. The shop floor sends the data to an IoT server, which is sitting in the cloud. That IoT server takes the data and gives it to a GPU or a very powerful analytics server, which crunches the numbers, and then it either gives you a feedback back to the shop floor, or it provides that information to the management where they can log in and check. And this is the overall architecture. This could be either based on internet, where you actually are going to the internet, or if you are very secretive, you could have your own intranet, and you don't really ever have to go out. It can provide you details of many, many aspects. So this is some of the things which we are able to provide. It's a non-intrusive system which we have, so you can just keep running. So the basic idea is that you don't want disruption if you are into production. You don't want any disruption to happen when you deploy something on it. You want to deploy sensors, you want to put things, and if you have to stop your production for one day, or you have some intrusive device which has to open your wires, this, that, you don't really want. You don't want to give access to your controllers. So that is where these are the techniques which do not have any intrusion. They're very advanced analytics, both on board on the IoT devices as well as backend. So you don't always have to send all the data backend. You can actually analyze the data and send it backend. A single user interface, whether it is the operator, the shift manager, or the general manager, or the CEO, they can all look at the same data from the single interface. Of course, based on their level of access, they will have different visibility. So one will be, the manager will be able to see all the shops, all the machines on the shop floor, whereas the operator will only see his or her shop, or his or her machine. And it's of course possible to be integrated to the ERP. So for instance, currently we have integrated it with, with the calendar. We know the operator, job ID, and aspects associated with this. So this is something which is deployed at several places, and I feel this is the next step which the tool room should be taking forward. However, if you have to do such an investment, there has to be a reason behind it. Now, to give a more specific understanding, ability to interact with and expand the capabilities of manufacturing through cyber-physical systems, the Internet of Things, and data analytics is what really we are asking the tool rooms to adapt. But adaptation means that there is a cost associated with it. So what really are the major initiatives, and why should we be doing this? Now, this is something which is driven around the world. In India, Samarth Udyog is one aspect where Ministry of Heavy Industries is trying to propagate and promote this same concept in India. But the key aspect is that if you look at in terms of the major activities which a tool room does, you have designing of tools, manufacturing, repair of tools, you have a stock inventory, you inspect them, and you finally distribute them. All of these activities can be completely changed if you have this kind of systems available in your tool room. Now, if you look at the data, the very first thing is that you will ask, do I have the data for that? And this is something which I am surprised, because whenever we go to a company, they say, well, we are not producing any data. How will you do data analytics on it? And this is something which is completely a misnomer, because if you look at a simple tool room, you go to any tool room, you'll realize they have design data on the computer logs. They have previous work order data, they have stock inventory data, they have inspection data, and historic stock inventory data, delivery records data, HR shift data. All of this is actually very, very important data. As someone has said, the next war will be, the world war will be fought because of data. It means data must be having some value. If data is having some value, ask yourself a question. It's like money, cash. You want to just keep the cash with you, or you want to put it to a good use? Should the cash not be money, not be earning money for you? So that's the same thing. You have so much of data, you just can't sit on it. This data should work for you. There is, of course, some investment required when you go to smart sensors, IoT devices, and you install that data. So apart from all the others, only one requires investment, rest of the things you already have, and let that data work for you. So what will be the key drivers? If you have to invest something, you have to do some analytics, you really don't want to do unless there's something to look at the return on investment. So what are the key things which it will provide you? It will provide you increased productivity, reduced cost, improved quality, reduced time to delivery. And I saw all of these were like great words just spoken in the last panel discussion, and increased safety. So these are the key basic drivers. A very small investment in usage of data and analytics, and you'll be able to achieve unprecedented highs. You'll be able to optimize and make your system work at the most efficient thing. And I'll just probably take now next couple of minutes, if I have that. So process optimization, energy utilization, consumption, real-time optimization, smart sensors, and IoT. So this is how you can do the process optimization in your tool rooms. Better asset utilization, your CNC machines, are they being properly used? I recollect I went to a very big aerospace manufacturer who was looking at buying almost half a dozen 5-axis CNC machines. And I was surprised because that OEM had more than 400 CNC machines in their shop floors. And I was surprised that are all the machines being completely utilized, that you want to buy 6 more new machines? And he said, well, I have no real-time data to see what were the assets utilizations. So you need to have a better understanding of that. Are your assets being fully utilized? Agile routing, machine flexibility, remote monitoring and control, and predictive maintenance. These are all things which are possible once you deploy smart manufacturing. Optimized human resource utilization. Smart human resource utilization. If you expect that there will be some times when you'll have very large requirements of production, you could utilize, and all of this will be available to you through the data which is available to you. Human-robot AI collaboration. You don't have to replace a human being, which is the very first other problem, that, oh, I'll have everything done automated. No, you don't want robots. You want something which is assisting humans rather than replacing humans. Remote monitoring and control and automation of repetitious work. Humans, they get really bored. They leave once they're not engaged. Why? Because they have to do the same repetitious work. Things which are repetitious are, number one, going to put the morale of HR down. They're also very prone to having errors, so you will have more errors if that's the case. So that can be something which could be automated. Smart inventory, real-time inventory. You have RFID tags and RFID technology. You can actually know where exactly your part is at what location. Now just imagine 20 years back when you used to courier something, you used to have a courier and you used to just wait that the courier will hopefully reach the other person. Today what you do, the moment you courier, you SMS or WhatsApp the courier ID or the other tracking ID, and the person actually tracks every single location. So now just imagine if you are a tool room which provides that service to your customer. The moment the customer places an order for a specific tool, you say, you know what, I'll have a 360-degree visibility of your order to you real time. You'll get to know when the person is working on that, when the design is ready, when the design is approved, when it has gone for manufacturing, when is it being inspected, and when it is being delivered. That will be a big game changer. It will give you a competitive edge which would not otherwise exist. So these are all little things which you have to do to get phenomenal benefits. Quality optimization, upstream anomaly. You can see there's something strange happening. You see an anomaly in the upstream. You don't have to wait till the final product has happened. You don't have to do so much of rework. Quality trends, things usually don't happen right away. If your tool is wearing and your sharpness is reducing, your surface roughness is increasing, it doesn't happen that you suddenly realize the tool is bad. You are able to grade and see the trend happening. Once you start seeing the trend happening, you say, you know what, now my quality will become so bad in maybe 3 days or so, so I need to change tool or do something. And all of these things are in your hand's reach. Smart inventory, I just talked about. Oops, I'm going the wrong way. Time to market. Now, this is something I feel the biggest differentiator, and I'm sorry, we are not, of course, a very big player, but whenever we approach a tool room for getting any tool made, we realize that the time to delivery is something which maybe we are very small as institute, but this can be really very precisely done. You'll have predictive maintenance and repairs, so you'll be able to go to time to market, you'll be able to demand, you will be able to forecast the demand, you can do concurrent engineering, and smart resource allocations to have a very speedy time to market. And finally, the sales and after sales, service and after sales. So just imagine that you send a tool to someone and you know exactly what the life of it is, and you know when that tool will come back for repair to you. Moreover, if you have embedded sensors, you'll be able to say that, you know what, your tool is being overused, and maybe it will be coming before time. So you can do predictive maintenance, you can do remote monitoring, you can make your resources available that, you know what, such a tool is about to come, I'll have to make my resources available for that. So there are endless possibilities. Now just last few things, that sensor technology has increased, communication and storage has increased, communication and computational hardware has changed, and data analytics has changed. So these are the 4 technological drivers, which is why we are standing here and talking about this. This was not there 10 years back, but today we can do that. And this is something which is really giving an opportunity, but at the same time a challenge. This is just to show you that from one camera on a city, you can observe 100 square kilometers of area at a resolution that you can see an individual person. I do not know if it's seen. You can see this individual person waving his or her hand. All possible because of data analytics. Because of data analytics and computation, you can see the image which you are seeing by just an MRI. So now we can actually go beyond and look at things, what you are thinking in your brain, all because of data analytics. We can do lip reading better than any human being. When I say we, I mean the AI systems can do that. And this is all possible because of the sensors, computational algorithms, and finally the analytics algorithms. Self-driven cars. Actually, self-driven cars are not very far. I just heard in the last session that self-driven cars are very far. No, I don't think so. As a matter of fact, self-driven cars will be something which can be put on your car. It's like a kit. You had a CNG kit, you can go here, take your car, and they will put a CNG kit. That's exactly what will happen. You can take your car, they can put a self-driving kit on it. And these are some of the examples. 13 million kilometers done by Google Car. Pizza is being delivered in US by Domino's through their autonomous vehicle, if you want. And this is happening for a year, almost a year plus. So now these things are phenomenal opportunities, but at the same time, they have some challenges in terms of social, jobs, and other aspects. You have Duplex, Google Duplex, which can have a human-sounding sound bot. So you could actually have a conversation, maybe 2 years from now, it would not be me standing here, you could have a bot which could talk to you in real time and give you this kind of a gyan. So now in my concluding remarks, smart manufacturing essentially offers phenomenal opportunities with a very little investment. However, there are a lot of challenges which exist, and these challenges have to be addressed specifically to the needs of India. We can't adapt what is being done in Germany, for instance, where the population is really very small and you don't have enough workers. Here we have other problem. We have manufacturing as a sector which is employing the maximum number of workers. So we can't adapt a solution which is working in Germany and Japan. We'll have to have our own solutions. So there are challenges of that kind which we have to look at. But finally, the most important part is the data. So we have to be very critical about data and be very cautious about it, that even before we deploy these technologies, we should make sure that our data is not getting lost. So with that, I'll stop and I'll thank you all for your attention. Thank you.
Mr. Ramani, can you please join us on stage to hand over a memento? Ladies and gentlemen, we would like to say a big thank you to Professor Asim Tewari for that wonderful presentation. Chair Professor in the Department of Mechanical Engineering and Head of the National Center for Aerospace Innovation and Research, Professor Asim Tewari.